Imagine waking up tomorrow morning and walking outside to feel the warmth of not one sun, but two. Imagine looking up into the sky and seeing a second blazing orb hanging where Jupiter used to be. A second dawn rising in the east while the original sun already climbs the western horizon. Imagine the shadows pointing in two different directions at once, the night sky forever banished, and every creature on Earth, every ecosystem, every ocean current, every weather pattern, every human civilization scrambling to make sense of a cosmos that has been fundamentally, irreversibly altered. Now ask yourself this: is that even possible? Could Jupiter, that massive, striped, storm-racked giant lurking out beyond the asteroid belt, ever ignite into a true star? And if it did, what would actually happen to us? What would happen to the Earth, to the Moon, to Mars, to every planet in the solar system? Would we survive? Would we thrive? Or would we be reduced to cinders floating in the void between two dying fires? This is not a fantasy. This is not science fiction. This is a question that some of the greatest minds in planetary science, astrophysics, and cosmology have seriously explored, debated, and modeled. And the answers, the real peer-reviewed, mathematically grounded answers, are simultaneously more terrifying and more astonishing than anything a screenwriter could dream up. Because the truth about Jupiter, about what it is, what it nearly was, and what it could theoretically become, sits at the very edge of human understanding. It forces us to look at our own star, at our own fragile blue world, and ask a question that cuts right to the core of our existence. How close are we, right now, to living in a completely different kind of solar system? So buckle in, because we are about to take a journey through the physics of stellar ignition, the deep history of our solar system's most dramatic near misses, the real science of what a second sun would do to our planet on day one, week one, year one, and century one. We're going to look at the biology, the geology, the climatology, the mythology, the philosophy, and the raw, unfiltered terror and wonder of a scenario that sits just outside the boundary of what our universe allows, but only just. And that closeness, that razor-thin margin between our solar system and something utterly alien, is the most astonishing thing of all. Let's start at the very beginning, because the beginning of this story is not where most people expect it to be. Most people, when they hear the question about Jupiter igniting, immediately think about the movie 2010, the year we make contact, the sequel to Stanley Kubrick's 2001, A Space Odyssey. In that film, based on Arthur C. Clarke's brilliant novel, an alien intelligence transforms Jupiter into a second sun, and the monolith-driven process kickstarts life on Europa, Jupiter's ice-covered moon. It's one of the most visually stunning and emotionally resonant sequences in science fiction cinema. And Clarke, to his enormous credit, actually grounded this fictional scenario in genuine scientific questions about Jupiter's nature. But the real story, the actual physics of why Jupiter can't ignite, why it came surprisingly close to being something very different, and what would happen if some unimaginable force somehow made it happen anyway, that real story is far more layered and far more astonishing than Clarke's already remarkable vision. To understand any of this, you first have to understand what Jupiter actually is. Not in the casual sense. Not the, it's a big planet with a red spot, understanding that most of us carry around from elementary school. You need to understand Jupiter at the level of its atomic constitution, its internal structure, its thermal history, and its gravitational biography. Because once you understand what Jupiter truly is, the question of whether it could ignite transforms from a simple yes or no physics problem into something much more philosophically profound. Jupiter is, by almost any reasonable measure, the most dominant object in our solar system after the Sun. Its mass is 1.898 times 10 to the power of 27 kilograms. That number is essentially meaningless to the human mind without some context, so let's provide that context. Jupiter is more massive than all the other planets in our solar system combined. Not just more massive than any single one of them, more massive than all of them put together. More than twice as massive, in fact. If you took every other planet, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and added up all their mass in one pile, Jupiter would still outweigh that pile by a factor of more than 2. It contains roughly 71% of all planetary matter in our solar system. It is, in the most literal sense, the king of the planets, and that title is not merely ceremonial. Jupiter's gravitational influence shapes the orbits of everything else. It has acted as a cosmic shepherd, a gravitational bodyguard, and at various points in the history of the solar system, as a wrecking ball that hurled smaller bodies into chaotic new trajectories. But here is the thing that most people never fully internalize. Jupiter is not made of rock and metal the way Earth is. Jupiter is made almost entirely of the same stuff the Sun is made of. Its composition is roughly 75% hydrogen by mass and about 24% helium, with trace amounts of methane, water vapor, ammonia, and other compounds making up the remaining 1%. Hydrogen and helium, the two most abundant elements in the universe. The two elements that make up virtually every star that has ever burned in the history of the cosmos. Jupiter is, at its most fundamental chemical level, star stuff. It is built from the same raw material as our Sun. And that is the fact that makes the question of its ignition so haunting, so persistent, and so genuinely fascinating. Because the difference between a star and a giant planet, at its most reduced essence, is not a difference of kind. It is a difference of quantity. It's a difference of mass. It's a difference of how much material collapsed together in that original nebular disk 4.5 billion years ago. Think about what that means. Think about how arbitrary that sounds. Whether something becomes a star that lights up the cosmos, or a dark, cold, swirling ball of gas that spends billions of years doing nothing but generating a faint internal warmth from gravitational compression, that distinction comes down to how much raw material happened to be in the neighborhood when things started clumping together. Jupiter didn't become a star not because it was made of the wrong stuff, but because there wasn't quite enough of the right stuff. It was like a campfire that someone almost lit, that had plenty of wood, but not quite enough kindling to get things going. And the gap between almost a star and actually a star is precisely what we need to examine, because it tells us everything about both the possibility and the impossibility of Jupiter's ignition. The process by which stars ignite is called nuclear fusion. Specifically, hydrogen fusion. The process by which hydrogen nuclei are forced together under conditions of extreme temperature and pressure to form helium nuclei, releasing enormous amounts of energy in the process. This is the process that powers the Sun. Every second, the Sun converts approximately 600 million metric tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to roughly 4 times 10 to the power of 26 watts. That is 400 septillion watts, which is a number so large it almost loses meaning. The energy released by the Sun every single second is greater than the total energy consumption of human civilization over its entire history by a factor that is almost inconceivably large. For nuclear fusion to occur, conditions must be extreme. The core of a star must reach temperatures in the range of 10 million Kelvin, 10 million degrees Celsius at minimum, and pressures so intense that the electron shells of atoms are stripped away, leaving bare nuclei exposed to one another. Under those conditions, the electrostatic repulsion between positively charged protons, the force that normally keeps atomic nuclei from coming anywhere near each other, can be overcome by quantum tunneling, and the strong nuclear force takes over, fusing nuclei together and releasing the binding energy that Einstein's famous equation describes. This is the process. This is the fire at the heart of every star. Now, the critical question: can Jupiter achieve those conditions? Can the temperature and pressure at its core ever reach the ignition threshold for hydrogen fusion? And here is where the physics becomes both humbling and extraordinary. The answer, as far as current science understands it, is no, not by a very comfortable margin. Jupiter's core temperature is estimated to be between 30,000 and 50,000 Kelvin, depending on the model and the assumptions used. That is genuinely hot, hotter than the surface of many stars, which itself is a remarkable fact. But it is still roughly 200 times too cold for the hydrogen fusion that powers main sequence stars like our Sun. The pressure at Jupiter's core, while staggering by any human standard, is also insufficient by several orders of magnitude to drive sustained hydrogen fusion. But here's where the story gets more interesting, because hydrogen fusion is not the only kind of nuclear fusion. There is a lower threshold process called deuterium fusion, which requires significantly lower temperatures and pressures, on the order of 1 million Kelvin in the core, rather than 10 million. Deuterium is a heavier isotope of hydrogen, with 1 proton and 1 neutron in its nucleus instead of hydrogen's single proton. Deuterium fusion can occur at conditions much more accessible than standard hydrogen fusion, and it is the fusion process that characterizes a class of objects called brown dwarfs. Brown dwarfs are the fascinating middle ground between giant planets and true stars. They are too massive to be classified as planets under current definitions, but not massive enough to sustain the full hydrogen fusion that powers main sequence stars. They glow faintly in infrared light, generating heat through a combination of gravitational compression and, in younger and more massive examples, deuterium fusion. They cool over millions of years, eventually fading into cold, dark objects sometimes called black dwarfs, though that term is also used for the theoretical end state of white dwarf stars, creating some definitional confusion in the literature. Brown dwarfs are in many ways the most philosophically interesting objects in the universe, precisely because they straddle the line between planetary and stellar in the most uncomfortable and definitionally challenging way. And here is the number that will genuinely shock you, the number that transforms this from an abstract physics discussion into something viscerally real. To become a brown dwarf, to cross that threshold from giant planet to something that at least generates its own heat through deuterium fusion, an object needs to have a mass of at least 13 times the mass of Jupiter. 13 Jupiters. That sounds like a lot, doesn't it? If Jupiter needs to be 13 times more massive to even begin the lowest threshold nuclear fusion process, then surely the idea of Jupiter igniting is purely theoretical nonsense. But wait. Wait and think about this carefully. Because 13 times Jupiter's current mass is still only about 1.25% of the Sun's mass. The range of masses between definitely a planet and definitely a star spans from roughly 13 Jupiter masses to roughly 80 Jupiter masses. At 80 Jupiter masses, an object can sustain true hydrogen fusion and qualify as a true main sequence star. So the entire range of brown dwarf masses sits between 13 and 80 Jupiter masses. And our Sun is about 1,000 times Jupiter's current mass. So yes, Jupiter is nowhere near the threshold. But consider this, Jupiter is also remarkable precisely because of how close it came, in the context of the early solar system's formation, to being something other than what it is. Let's go back to the beginning. 4.5 billion years ago, the region of space now occupied by our solar system was a vast cloud of gas and dust, a molecular cloud rotating slowly in the outer arm of the Milky Way galaxy. Something disturbed this cloud, perhaps a nearby supernova, perhaps a gravitational interaction with another cloud, and it began to collapse under its own gravity. As it collapsed, it spun faster, the way a figure skater pulls their arms in to spin more quickly. Conservation of angular momentum. The collapsing cloud flattened into a disk, and at the center, material concentrated into the dense, hot protosun. Around this central concentration, the disk of remaining material, the protoplanetary disk, began to structure itself. In the inner regions of this disk, where temperatures were high, only materials with high melting points could condense into solid particles, silicates, metals, minerals. These particles gradually clumped together through a process called accretion, building up the rocky inner planets. In the outer regions of the disk, beyond a boundary called the frost line or snow line, roughly 2.5 astronomical units from the Sun, in the region of the asteroid belt, water ice could exist as a solid. And with ice available as building material, the outer solar system had access to vastly more solid material than the inner solar system. Jupiter formed in this outer region, beyond the frost line, accreting a massive rocky icy core of perhaps 10 to 20 Earth masses. And then, critically, this core was large enough to gravitationally capture the gas of the surrounding disk. Hydrogen and helium poured inward, adding to Jupiter's mass at an extraordinary rate. This process of runaway gas accretion was rapid by astronomical standards, occurring over perhaps 1 to 10 million years. And here is the crucial historical contingency. had the solar nebula contained a somewhat larger amount of material in Jupiter's orbital region, or had Jupiter's core formed somewhat faster, capturing more gas before the protosun's radiation cleared the disk, Jupiter could have accreted significantly more mass. Not 13 times more mass, certainly. But there are models that suggest, under slightly different initial conditions, Jupiter could have become significantly more massive than it is. Meanwhile, there are also models suggesting that in binary star systems, systems with two stars, which are actually more common than single star systems in the galaxy, one of those stars could be as small as 80 Jupiter masses. Jupiter, at its current mass, is only about 13 times too light to begin deuterium fusion, and about 80 times too light to be a true star. In the grand, vast scale of possible masses in the universe, Jupiter sits frustratingly, tantalizingly close to the lower boundary of something more. Now ask yourself this question, and really sit with it. How different would your life be right now if, 4.5 billion years ago, there had been just a bit more gas available in the outer solar nebula? If Jupiter had accreted enough to become even a dim brown dwarf, would Earth even exist? Would the inner solar system have formed the same way? Would life have emerged on our planet at all? The history of the universe is littered with these hinge points, these moments of almost where the difference between a universe with life and a universe without it, between a planet with observers and a planet without them, comes down to something as seemingly mundane as the local density of gas in a cloud a few light years across. It is humbling in a way that almost nothing else in science can match. But let's push forward, because the really extraordinary stuff is still ahead. Let's ask the question directly now. What if, by whatever mechanism, alien technology as in Clarke's novel, a rogue planet crashing into Jupiter and adding mass, or simply a thought experiment we're choosing to conduct, Jupiter did ignite? What would actually happen? Let's build this scenario step by step, because each stage of the ignition and its aftermath has its own distinct character, its own specific implications for Earth and the rest of the solar system, and its own set of genuinely astonishing consequences. Stage 1 is the ignition event itself. For Jupiter to ignite as a star, a true hydrogen-fusing main sequence star, its mass would need to increase by a factor of roughly 80. This is physically impossible under any natural mechanism operating on human timescales, and almost certainly impossible even on geological timescales without some extraordinary intervention. But let's say, hypothetically, that this mass is somehow added. Let's say Jupiter becomes a red dwarf star, the smallest, faintest class of true hydrogen-fusing stars. Red dwarfs are incredibly common. Current estimates suggest that red dwarfs make up somewhere between 70 and 80% of all stars in the Milky Way. They are dim, long-lived, and relatively cool by stellar standards. Their surface temperatures range from about 2,500 to 4,000 Kelvin, compared to the Sun's surface temperature of about 5,778 Kelvin. They are orange-red in color, sometimes described as burning embers compared to the Sun's brilliant white-yellow flame. A red dwarf at Jupiter's distance, about 5 astronomical units from Earth, or roughly 5 times the Earth-Sun distance, would be an extraordinary presence in our sky, but it would not be the blinding, overwhelming second sun of science fiction. It would be more like a large, dim, reddish star, strikingly bright in the night sky but not challenging the sun's dominance during daytime. Now, if Jupiter only became a brown dwarf, if it crossed that lower threshold of 13 Jupiter masses through some hypothetical mechanism, it would be even dimmer. Brown dwarfs emit primarily in infrared radiation, with very little visible light. From Earth, at Jupiter's current distance, a brown dwarf Jupiter might appear as a very bright star, brighter than anything currently in our night sky, perhaps comparable to a crescent moon in terms of light delivery to Earth's surface, but nothing like a second sun. The night side of Earth would be dimly illuminated. Some plants might be able to photosynthesize in this faint additional light, but the effects on Earth's climate would be relatively modest compared to the full stellar ignition scenario. But let's keep going with the full ignition scenario, because it's far more dramatic and far more revealing of the deep physics involved. Let's say Jupiter becomes a red dwarf of minimal stellar mass, roughly 80 Jupiter masses, or about 8% of the Sun's mass. This is the smallest possible true star. What happens in the moments, the hours, the days after ignition. The first thing to understand is that the ignition itself would be an event of almost incomprehensible violence. The initiation of sustained nuclear fusion in a mass of hydrogen-rich gas would release energy on a stellar scale in a very short time. A cosmic event that would generate an initial burst of radiation and a shock wave as the gas envelope of the new star rapidly heated and expanded. This initial burst, something like a stellar birth flash, would send a pulse of intense radiation outward across the solar system at the speed of light. At 5 astronomical units from Earth, light takes roughly 41 minutes to travel. So the flash of a newly ignited Jupiter would reach Earth 41 minutes after ignition. Before that flash arrived, we would have no warning at all. There would be no rumble of distant thunder, no preliminary trembling of the ground, no subtle change in the air. Just suddenly, a new light in the sky, growing from Jupiter's usual point of light to something enormously, terrifyingly brighter in minutes. What would that burst of initial radiation contain? In the very first moments, the newborn star would emit across the entire electromagnetic spectrum. Not just in visible light, but in ultraviolet radiation, X-rays, and potentially even some gamma-ray emission depending on the specifics of the fusion initiation. This initial burst would be analogous, in some ways, to the early phase of a solar flare or a coronal mass ejection from our own sun, but scaled up and sustained. The ultraviolet and X-ray components of this burst would interact with Earth's upper atmosphere. Our atmosphere is actually an extraordinarily effective shield against these high-energy forms of radiation. The ozone layer absorbs most incoming ultraviolet, while the upper atmosphere absorbs X-rays before they can reach the surface. So the initial burst, while genuinely intense, would not immediately fry everything on Earth's surface. But it would cause measurable damage to the ozone layer, a pulse of energy sufficient to break apart ozone molecules over the hemisphere facing the new star, temporarily thinning the protective shield and allowing more solar ultraviolet radiation to reach the surface in the weeks and months following the event. By the time this initial radiation burst had passed and settled into the steady emission of a stable red dwarf, the visible light component would be what most people first noticed and feared. Jupiter's new stellar luminosity, the total energy output, would be roughly a fraction of a percent of the Sun's total luminosity. Red dwarfs at the lowest end of the stellar mass scale emit somewhere between 0.01% and 0.1% of the Sun's total energy output. This might sound negligible, but let's calculate what it actually means at Earth's distance. At 5 astronomical units, the inverse square law tells us that Jupiter's light reaching Earth would be dimmer than it appears at Jupiter's own surface by the square of the distance ratio. Earth receives sunlight at 1 astronomical unit. Jupiter is 5 astronomical units from Earth on average. Actually, the distance varies as both planets orbit, ranging from about 4 to about 6 astronomical units, but we'll use 5 as a working average. The inverse square law means that the intensity of light at Earth's distance from Jupiter is 25 times less than at Jupiter's own surface. So even a red dwarf with 0.01% of the Sun's luminosity, seen from 5 astronomical units away, would deliver to Earth's surface an amount of light roughly equivalent to. Let's do this carefully. The Sun delivers about 1,361 watts per square meter to Earth's upper atmosphere. This is called the solar constant. A red dwarf with 0.01% of the Sun's luminosity, that's 1/10,000th of the Sun's luminosity, would deliver, at 1 astronomical unit, about 0.1361 watts per square meter. At 5 astronomical units, dividing by 25, you get roughly 0.005 watts per square meter. That is about 5 milliwatts per square meter, roughly equivalent to the light delivered by a full moon, which delivers about 0.001 watts per square meter. So actually, a minimal mass red dwarf Jupiter would be considerably brighter than the full moon, but not the devastating second sun of catastrophist scenarios. It would be remarkable, uncanny, transformative in many ways, but not immediately lethal to Earth's surface life from the light component alone. However, and this is crucial, the numbers I've just given you are for the steady-state emission of a stable red dwarf. The real danger, especially in the early period of a newly formed star, is not the steady emission but the variable emission. Young stars, and especially small red dwarf stars, are notoriously flare-prone. Solar flares from our own sun are already a concern for satellite communications, power grids, and astronaut safety. Red dwarf flares can be proportionally far more intense relative to the star's baseline emission, releasing energy equivalent to many times the total energy output of the star in a burst lasting minutes to hours. If a new red dwarf Jupiter were as flare-active as many observed red dwarfs are, Earth could be subjected to intense radiation bursts that would far exceed the steady-state light calculations I just described. These flares could cause significant additional ozone depletion, disrupt electrical infrastructure, and deliver elevated ultraviolet and X-ray doses to the surface. The question of whether Earth's magnetic field and atmosphere would adequately protect surface life in such a flare-active environment is a genuinely difficult one, and the answer is probably mostly yes. Earth's magnetic field and thick atmosphere are robust shields, but mostly is doing a lot of work in that sentence when we're talking about the survival of civilization. But the light and radiation are only part of the story. Let's think about heat. Would a Jupiter-as star warm up the Earth significantly? The thermal contribution of a red dwarf at 5 astronomical units is small relative to the Sun's contribution, but it is not zero. Adding a few thousandths of a watt per square meter to Earth's energy budget might not sound like much, but climate is an enormously sensitive system. Small changes in energy input can, over time, drive significant changes in temperature, circulation patterns, ice coverage, and precipitation. The added warmth from even a dim Jupiter star would be most noticeable on the hemisphere of Earth facing Jupiter during nighttime, effectively ending dark, cold nights for those regions. The perpetual faint light would inhibit the normal nocturnal cooling of Earth's surface, potentially raising nighttime temperatures slightly. Over decades and centuries, this cumulative warming effect could compound, and the effects on the hemispheres would not be symmetric, because Earth is rotating. All regions of Earth cycle through periods of facing toward and away from Jupiter, though the geometry would make some latitudes experience the effect differently than others based on the relative positions of the Earth and a now luminous Jupiter in the solar system. Now let's zoom out and think about what a second stellar body would do to the gravitational architecture of the solar system. This is where things get genuinely destabilizing, and not in the dramatic, immediate catastrophe sense, but in the deep, slow, geological timescale sense that may ultimately be more consequential for life on Earth than any of the radiation or heat effects. Our solar system is not simply the Sun with planets orbiting it. It is an extraordinarily complex gravitational system in which the Sun's dominant gravity keeps everything roughly in place, but in which the gravitational interactions between all the bodies, the planets, the moons, the asteroids, the comets, the Kuiper belt objects, constantly nudge and tug at one another. These interactions are generally small, and their effects unfold over millions to billions of years. But they are real, they accumulate, and under our current conditions they have been understood and modeled with remarkable precision. We know, for example, that Jupiter's current orbital configuration has been stable for billions of years, and that its gravity has played a role in sculpting the asteroid belt, stabilizing Earth's axial tilt, in combination with the Moon's influence, and deflecting comets and asteroids away from the inner solar system, acting, as many astronomers describe it, as a gravitational shield for Earth. Now imagine that Jupiter, instead of being a large, dark, cold giant planet at 5 astronomical units, becomes a star with significant mass, 80 Jupiter masses, or roughly 8% of the Sun's mass. This is not a small change to the gravitational balance of the solar system. This is a massive perturbation. The gravitational pull of a body 80 times Jupiter's current mass, acting on everything else in the solar system, would be 80 times stronger than Jupiter's current gravity. The effects on the asteroid belt would be immediate and severe. Asteroids currently in relatively stable resonant orbits with Jupiter would be flung into chaos. The Kirkwood gaps, the zones in the asteroid belt currently cleared by Jupiter's gravitational resonance, would be restructured as the new mass distribution reorganized the resonance zones. Many asteroids currently in stable orbits could be thrown into Earth-crossing trajectories, dramatically increasing the rate of asteroid impacts on Earth. This is not a small concern. Increased asteroid bombardment over geological timescales has been a major driver of mass extinctions in Earth's history. The Late Heavy Bombardment, a period of intense asteroid impacts roughly 3.9 billion years ago, is thought to have been triggered partly by rearrangements in the orbits of the outer planets. A sudden, massive increase in Jupiter's gravitational pull would potentially trigger a new bombardment period that could rival or exceed the original one. The effects on the other outer planets would also be profound. Saturn, Uranus, and Neptune all orbit in the gravitational shadow of Jupiter to varying degrees, and their current orbital configurations are products of billions of years of stable interaction with Jupiter as it currently exists. An 80-fold increase in Jupiter's mass would destabilize all of these orbits to some degree. The most vulnerable would be whatever bodies currently occupy resonant relationships with Jupiter, objects whose orbital periods are simple fractions of Jupiter's orbital period. Resonance can stabilize or destabilize, depending on the configuration, and the sudden change in Jupiter's mass would break current resonances and establish new ones, potentially in configurations that are dynamically chaotic rather than stable. There is also the question of what happens to Jupiter's moons. The Galilean moons, those extraordinary worlds that Galileo first observed in 1610, and which have since proven to be among the most geologically and astrobiologically interesting objects in the solar system. Io, Europa, Ganymede, and Callisto. These four large moons would, in the ignition scenario, find themselves orbiting not a planet but a star. Their orbital dynamics, currently determined by Jupiter's gravity, would be restructured by the enormous tidal forces of a stellar mass object. Io, which currently experiences such intense tidal heating from Jupiter that it is the most volcanically active body in the solar system, would face tidal forces 80 times more intense, if it survived at all. The extreme tidal forces from a stellar mass Jupiter might well tear Io apart entirely, or heat it so intensely that it partially or fully melted. Europa, with its subsurface ocean of liquid water kept warm by tidal heating from Jupiter, would also experience dramatically increased tidal forces, though in this case, the additional heat might actually make Europa's subsurface ocean warmer and deeper, and the additional light from a stellar Jupiter might even warm Europa's icy surface. There is a poignant irony here. The very process that makes Europa's ocean deeper and more extensive might also be the process that makes life there, if it exists, more possible. Arthur C. Clarke intuited this in his novel, and while his specific mechanism was fantastical, his intuition about the directionality of the effect was not unreasonable. But let's come back to Earth for a moment, because there's a critical aspect of the ignition scenario that most popular treatments handle very poorly. The sky. What would the sky actually look like? What would a person standing outside experience, see, feel? Let's paint this picture in as much detail as the science allows, because the human experience of this event is as important as the astrophysical analysis. At the moment the light from ignition reached Earth, 41 minutes after the event itself, the first sign would be a sudden brightening of the point of light that observers would recognize as Jupiter. Jupiter is already easily visible to the naked eye in our current sky. At its brightest, it is actually the third brightest natural object in the sky after the Sun and the Moon, shining at a magnitude of around -2.94. But even at that brightness, it is still just a point of light, a very bright star in the sky, but not something that casts meaningful shadows or illuminates the landscape. The new stellar Jupiter would initially appear to brighten from that familiar point of light over the course of minutes, growing first from a bright star to something resembling Venus at its closest approach, then to something like a half-moon in terms of apparent brightness, and then, if we're talking about a full red dwarf and not just a brown dwarf, potentially to something significantly brighter than any object in our sky except the Sun itself. But it would remain a point source of light, not an extended disk like the Sun or Moon, because at 5 astronomical units distance, even a red dwarf star has an angular diameter of only a fraction of a degree as seen from Earth, compared to the Moon's apparent half-degree diameter. You could cover the new stellar Jupiter with the tip of a finger held at arm's length. But that intense point of red-orange light would be enough to cast shadows. At night, everything on the hemisphere facing the new star would have a faint orange-tinted shadow. Not the crisp, defined shadow you cast on a sunny day, but the kind of diffuse directional shadow you might see under a full moon, except slightly warmer in color and slightly more orange. Day would still be day, dominated by the sun, but night would never be truly dark again for anyone on the hemisphere with a view of the new stellar object. The stars would still be visible. The light from the new star would not be enough to wash out the starfield the way moonlight does to some extent, but the sky would have a permanent faint orange glow when the new star was above the horizon. From mid-latitudes, this would be most of the night for many months of the year, depending on the relative positions of Earth and the new stellar system. The psychological and cultural impact of this change would be as significant as the physical impact, and I want to spend some time on this because it is a dimension of the scenario that is almost never explored seriously. Human beings have navigated by the stars for our entire existence as a species. Our mythology, our religion, our philosophy, our art, our sense of our place in the cosmos. All of it has been shaped by the sky as it exists. The sudden appearance of a new star, not a nova or supernova that brightens for weeks and then fades, but a permanent new stellar companion to our solar system, would be an event without precedent in recorded human history, and possibly without precedent in human prehistory as well. It would shatter the distinction between day and night in a way that would be immediately felt by every species on Earth. Consider the biological impact first. Life on Earth has evolved under the rhythm of day and night, a roughly 24-hour cycle of light and darkness that governs the sleep-wake cycles, the hormonal rhythms, the feeding patterns, the reproductive cycles, and the migratory behaviors of virtually every complex organism on the planet. This is called the circadian rhythm, and it is so deeply embedded in the biology of living things that it operates at the cellular level, driven by molecular clocks that have been conserved through hundreds of millions of years of evolution. The introduction of a permanent faint light source that eliminates truly dark nights, even if that light source delivers less illumination than the full moon, would disrupt circadian rhythms across the entire kingdom of life. Insects that navigate by the stars would be confused. Nocturnal predators whose eyes are adapted to operate in true darkness would be at a disadvantage. Migratory birds that use the night sky for navigation would be thrown off course. Sea turtles that navigate by the stars to reach nesting beaches would be disoriented. The suppression of melatonin production in humans and other mammals during the night hours, already a concern due to artificial light pollution from cities, would be exacerbated planet-wide, potentially disrupting sleep quality and immune function on a global scale. But the disruption would not stop at individual biology. Ecosystems are built on the reliable cycling of day and night. Prey species depend on the cover of darkness to avoid predators. Predators depend on the darkness to approach prey undetected. Pollinating insects time their activity to day-night cycles. Flowering plants time their blooming and their nectar production to those same cycles. The coral reefs spawn their eggs in synchrony with the lunar cycle and the darkness of moonless nights. Every ecological relationship that depends on the reliable presence of true darkness would be stressed, disrupted, and in some cases catastrophically broken by a permanent additional light source in the sky. And then there is the human cultural dimension. Think about what this new star would mean to the world's religions. In virtually every human culture and religious tradition, the sky has been a locus of divine meaning. The stars, the sun, the moon, these are not just physical objects to the believing human mind. They are signs, portents, embodiments of divine will, or literally divine beings. The sudden ignition of Jupiter, the planet named for the king of the Roman gods, the planet that in other cultures was associated with the sky god, the thunder god, the supreme divine, into an actual burning star would be interpreted through every possible religious lens simultaneously. For some, it would be a sign of the end times. For others, a divine miracle. For others still, a moment of cosmic evolution, a celestial becoming. The diversity of interpretations would be immediate and intense, and the social, political, and potentially violent consequences of that diversity of interpretation, in a world already deeply divided by religion and ideology, are not pleasant to contemplate. Throughout history, unusual celestial events, eclipses, comets, novae, have triggered everything from mass conversions to wars to the sacrifice of human beings. A permanent new star would be a celestial event of incomparably greater magnitude than any of those. Let's also think about what would happen to Jupiter's existing moons in more detail, because they represent one of the most fascinating and complex subplots of this entire scenario. The solar system currently has, around Jupiter alone, 95 known moons as of the most recent counts from NASA and the scientific community. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are the most significant and the most studied. But all of them would be profoundly affected by Jupiter's transformation. Io, which orbits Jupiter at a distance of about 421,800 kilometers, closer to Jupiter than our moon is to Earth, currently experiences tidal heating due to the competing gravitational pulls of Jupiter, Europa, and Ganymede. This tidal heating already makes Io the most volcanically active body in the solar system, with over 400 active volcanoes and a surface that is constantly being resurfaced by lava flows and sulfur deposits. If Jupiter became a stellar body with 80 times its current mass, Io's tidal heating would increase by... Well, actually, the relationship is complex. Tidal heating depends on the mass of the primary body, the eccentricity of the moon's orbit, the moon's internal rigidity, and several other factors. But a rough scaling suggests the tidal heating would increase dramatically, potentially by factors of hundreds. Io could be heated so intensely that it became a molten, magmy ocean world, eventually losing its solid crust entirely and dissolving into a globe of liquid rock. The sulfur dioxide atmosphere that Io currently has, a tenuous, frost and gas atmosphere that is actually maintained by volcanic outgassing, would be blown away by the intense radiation and stellar wind of the new star. Io, as we know it, would cease to exist. Whether anything resembling a moon would remain in that orbit, or whether the tidal forces and heat would reduce Io to a dispersed cloud of vaporized silicates is a genuinely interesting question, though the physics suggests the moon would at least partially survive in some radically altered form for some period of time before potentially being broken up. Europa is the moon that excites astrobiologists most in our current solar system. Beneath Europa's icy crust, estimated to be somewhere between 10 and 30 kilometers thick, there is a liquid water ocean that contains more water than all of Earth's oceans combined. This ocean is kept liquid by a combination of tidal heating from Jupiter and residual radioactive decay heat from Europa's rocky interior. If Jupiter became a star, the tidal heating component would increase dramatically, warming Europa's ocean significantly. Additional heat from the stellar radiation would also begin to warm Europa's icy surface. Over time, the ice layer would thin and potentially melt away entirely, exposing a liquid water world, an ocean planet, for the first time in the solar system's history. This is an extraordinary image, a moon-sized ocean world, orbiting a dim red star at a distance of about 670,900 kilometers, its entire surface a global ocean of liquid water warmed by tidal forces and stellar radiation, with no solid land anywhere on its surface. Is this a habitable environment? Is this an environment where life could exist, or where existing life, if it exists in Europa's current subsurface ocean, could flourish? The answer is complicated. Life as we know it requires liquid water, an energy source, and chemistry, the right kinds of chemical compounds available in the right configurations. Europa's current ocean likely already provides all three of these. Tidal and possibly hydrothermal chemistry at the ocean floor probably provides chemical gradients that could drive metabolism. The water is liquid. The chemical inventory may be rich. If the ice crust were removed by Jupiter's stellar heating, sunlight, stellar light, from the new star would penetrate the surface ocean directly, potentially enabling photosynthesis in the upper water layers for the first time. This would dramatically expand the potential energy budget of Europa's biosphere, if one exists, and could in principle support a much richer diversity of life. But there is a catch, and it is a serious one. The removal of the ice shell that currently shelters Europa's ocean would also expose it to the radiation environment of a new star, and Jupiter as a star, especially in its early flare-active phase, would produce significant ultraviolet and particle radiation. While water is a decent shield against UV radiation, UV penetration in water is measured in meters, not kilometers. The surface waters would be sterilized unless Europa developed some other form of UV protection. And without an atmosphere capable of filtering radiation, Europa's current atmosphere is almost non-existent, essentially a thin shell of oxygen produced by radiolysis of the ice. The surface ocean would be a challenging environment for complex life, even as the deep ocean might be a refuge. Ganymede and Callisto, the two outer Galilean moons, orbit further from Jupiter and would experience less dramatic tidal heating changes. Ganymede, the largest moon in the solar system, larger than Mercury and nearly as large as Mars, already has a subsurface ocean of its own, detected by the Hubble Space Telescope through observation of its aurorae. Ganymede also has its own magnetic field, making it unique among moons in our solar system. A stellar Jupiter would warm Ganymede's surface and increase its tidal heating, potentially expanding its subsurface ocean and making it more accessible from the surface. Callisto, the outermost Galilean moon, has shown evidence of a subsurface ocean as well, though it is less well established. Both moons would be significantly warmed by stellar Jupiter, and both might become more interesting targets for the search for liquid water and potentially life. Now, let's step back from the moons and think about the broader solar system architecture again, because there is an aspect of this scenario that I haven't yet addressed, and that is genuinely critical. What happens to Earth's orbit? What happens to the orbital mechanics of the entire inner solar system under the gravitational influence of a stellar mass Jupiter? In a binary star system, a system with two stars, the gravitational dynamics are complex and depend critically on the separation between the two stars and the mass ratio between them. Our solar system would, after Jupiter's ignition, become a binary star system with an extremely unequal mass ratio. The Sun at 1 solar mass versus Jupiter star at roughly 8% of a solar mass, separated by about 5 astronomical units. This is actually a separation and mass ratio that falls within the range of observed binary star systems. Not a physically absurd configuration. Many real binary systems have similar or smaller separations with similar or larger mass ratios. In such a system, planets can orbit in two configurations. They can orbit one star in a tight orbit that is well within the gravitational sphere of influence of that star, called S-type orbits, or they can orbit around both stars in a large orbit well outside the gravitational influence of either individual star, called P-type or circumbinary orbits. Earth, at 1 astronomical unit from the Sun, orbits the Sun at a distance that is 5 times smaller than the Sun-Jupiter separation. This falls within the range of S-type orbit stability for a binary system with these parameters. Numerical simulations of binary star systems with similar mass ratios and separations generally show that planets in S-type orbits around the more massive primary star can remain stable if their orbital radius is less than roughly 1/5 to 1/3 of the binary separation. 1/5 of 5 astronomical units is 1 astronomical unit, which is exactly where Earth orbits. This is uncomfortably close to the stability boundary. Earth's orbit might be marginally stable in this configuration, meaning that it could remain in a quasi-stable orbit that is gradually perturbed over millions of years, or it could eventually become chaotic and be ejected from the inner solar system entirely. Or, perhaps more terrifyingly, flung into an orbit that carries it alternately closer to and further from the Sun, creating wild temperature swings that no complex biosphere could survive. The numerical simulations that have been done on this kind of system, and planetary scientists like David Kipping, Dmitry Veris, and others have done serious computational work on binary planet stability, suggest that the exact outcome would depend sensitively on initial conditions and the specific orbital configuration at the moment of Jupiter's ignition. Some configurations would leave Earth's orbit marginally stable for billions of years. Others would lead to Earth being ejected from the solar system within a few million years. And some would lead to Earth being captured into an orbit around stellar Jupiter, which is arguably the most extraordinary possibility of all. Think about what it would mean for Earth to be captured into an orbit around the new stellar Jupiter. Earth would no longer be a planet orbiting the Sun. It would become a moon of a star. It would orbit a dim red star at a distance of perhaps a few million kilometers, in a configuration roughly analogous to how some of Jupiter's current moons orbit it now, except with an Earth-sized body as the orbiting object and a stellar mass Jupiter as the primary. The climate of such an Earth would be radically different, tidally locked, potentially, with one hemisphere permanently facing the stellar Jupiter and the other hemisphere in permanent darkness, divided by a ring of perpetual twilight at the terminator. Or, if the orbit were eccentric rather than tidally locked, it might oscillate between periods of intense heating and periods of cold. Life as it currently exists on Earth would almost certainly not survive this transition. But could new forms of life eventually emerge in such an extraordinary environment? That is a question that stretches our understanding of biology to its limits, and the honest answer is, we don't know. Let's take a moment to step back even further and ask a genuinely important philosophical question about this entire scenario, because there's a dimension to it that I think deserves serious attention. The question is our solar system unusual in having a Jupiter-like body that did not ignite? Is the failure of Jupiter to become a star a typical outcome in solar system formation? Or is it something unusual about our particular system? The answer from current exoplanet research is genuinely interesting. The Kepler Space Telescope, launched in 2009 and retired in 2018 after discovering 2,662 confirmed exoplanets, revealed that planetary systems come in an enormous variety of configurations, many of them nothing like our own solar system. Hot Jupiters, Jupiter-sized planets orbiting extremely close to their parent stars, within a fraction of an astronomical unit, are found around a significant minority of Sun-like stars. Super-Earths and mini-Neptunes, a class of planets with no analog in our solar system, with masses between Earth and Neptune, appear to be the most common type of planet around other stars. Systems with multiple planets packed into very tight orbits, all smaller than Earth, are common. Systems that look anything like our solar system, with an inner zone of small rocky planets, a frost line, and outer gas giants, appear to be comparatively rare, though it's important to note that our survey methods are still better at detecting certain types of planets than others. What exoplanet research has also revealed is that binary star systems, systems with two stars, are extremely common, possibly more common than single star systems. Estimates vary, but roughly half of all star systems in the galaxy may be binary or multiple star systems. So the configuration that would result from Jupiter's ignition, a binary system with a large primary and a small secondary separated by a few astronomical units, is actually a fairly common configuration in the universe. In fact, several such binary systems are known to host planets, and some of those planets are in the habitable zones of one or both stars. The TRAPPIST-1 system, while not a binary, shows how small red dwarf stars can host Earth-sized planets. 7 of them, in fact, several in the habitable zone. The concept of a binary system with Earth-sized planets in stable habitable zone orbits is not science fiction. It is observed reality in other solar systems. This means that what we're really asking, in the "what if Jupiter ignited" scenario, is not what would a completely impossible thing look like. We're asking, what would our solar system look like if it had formed the way roughly half of all star systems in the galaxy form, as a binary? And that reframing is both humbling and exhilarating, because it means we are not exploring pure fantasy. We are exploring a path not taken, an alternative version of our solar system that corresponds to something that actually exists out there in the galaxy, around other stars right now. Somewhere in the Milky Way, there is almost certainly a binary star system with a large yellow sun and a small red companion, with a rocky planet in a stable S-type orbit around the primary star, perhaps with water on its surface and life in its oceans. That system is what our solar system might have been. And its people, if it has people, look up at night and see a second, dimmer sun, and perhaps wonder whether there are any systems out there with only a single star. Now let's talk about a specific and fascinating aspect of the Jupiter ignites scenario that is almost never discussed in popular treatments: what it would do to the asteroid belt. Because the asteroid belt is not just a collection of random rocks floating in space between Mars and Jupiter. It is a fossil record of solar system formation, a zone where a planet was never able to form because Jupiter's gravitational influence prevented the small bodies from accreting into a larger body. The total mass of the entire asteroid belt is only about 4% of the mass of the Moon, a remarkably small amount of material spread across an enormous volume of space. But the individual objects range in size from tiny pebbles to Ceres, the largest asteroid, which at 945 kilometers in diameter is large enough to have been classified as a dwarf planet. Jupiter's gravitational resonances currently maintain the asteroid belt in a roughly stable configuration, with certain orbital periods, those that correspond to simple fractions of Jupiter's orbital period, cleared of material, the Kirkwood gaps, while other orbital ranges are populated with stable populations. If Jupiter's mass were to suddenly increase by a factor of 80, all of these resonance structures would be violently disrupted. Asteroids in currently stable resonances would find themselves in unstable ones. Asteroids in currently chaotic resonances would find themselves in new stable ones. The overall effect would be a period of intense disruption, a reshuffling of the asteroid belt that could send significant numbers of asteroids into the inner solar system, dramatically increasing the rate of Earth impacts. How dramatically? This is something that planetary scientists have modeled in the context of the Grand Tack hypothesis, a theoretical model of early solar system evolution that proposes Jupiter migrated inward toward the Sun early in the solar system's history, then reversed course and migrated outward, the tack in sailing terms. This migration, according to the hypothesis, explains several features of our solar system's current configuration, including the small mass of Mars, the structure of the asteroid belt, and the composition of various populations of small bodies. The Grand Tack model involves Jupiter moving from about 3.5 astronomical units inward to 1.5 astronomical units before being pulled back out to its current location. And this migration is thought to have dramatically altered the asteroid belt, sending many bodies out of the belt and into new orbits. A sudden, massive increase in Jupiter's mass would have analogous disruptive effects, potentially producing a bombardment period that could rival or exceed the late heavy bombardment. During the late heavy bombardment, which occurred approximately 3.9 billion years ago, Earth experienced a dramatic spike in impact rates that left enormous impact basins on the Moon and likely had profound effects on the early biosphere of Earth. Some researchers have argued that this bombardment period might actually have been beneficial for life, delivering water, organics, and other biogenic molecules from the outer solar system. Others argue it was catastrophic, periodically sterilizing the surface of the Earth. The debate is ongoing. But a new bombardment triggered by Jupiter's ignition would be superimposed on an already complex, mature biosphere. A biosphere that has spent 3.5 billion years evolving and diversifying, building intricate ecological networks that are vulnerable to precisely this kind of abrupt disruption. The consequences would be severe and prolonged, potentially comparable to or exceeding the KPG extinction event, the impact 66 million years ago that killed the dinosaurs, but extended over a much longer period and affecting a much more diverse array of life. But here's a counterintuitive point that the scenario opens up, and it's one of the most interesting in this entire discussion. The bombardment, as destructive as it would be, is also a mechanism for delivering new material to the inner solar system. Asteroids from the outer parts of the belt, the carbonaceous chondrites, the C-type asteroids, are rich in water ice, organic compounds, amino acids, and other biogenic molecules. The current scientific consensus, based on isotopic analysis of Earth's water and on the composition of carbonaceous chondrite meteorites, is that a significant fraction of Earth's water was delivered by asteroid and comet impacts early in the solar system's history. A new bombardment period triggered by Jupiter's ignition could deliver additional water to the inner planets, potentially making Venus, Earth, and Mars more water-rich than they currently are. For Mars in particular, which is a cold, dry, nearly airless world today but was once wet and warm, a new bombardment could potentially deliver enough water to partially restore a liquid water environment on its surface. This is a genuinely wild possibility. Jupiter's ignition could, paradoxically, be one mechanism by which Mars became habitable again, even as it simultaneously devastated Earth's current biosphere. Let's take a moment to explore something that most people never consider when thinking about this scenario. What would happen to the comets? The comets of our solar system exist in two main reservoirs: the Kuiper Belt, which extends from the orbit of Neptune outward to about 50 astronomical units, and the Oort cloud, a vast spherical shell of icy bodies that extends from about 2,000 astronomical units out to perhaps 100,000 astronomical units, nearly 2 light-years from the Sun. The Oort cloud is thought to contain trillions of cometary nuclei, and it is the source of long-period comets that occasionally fall inward toward the Sun on journeys of tens of thousands of years. Jupiter's gravitational influence currently plays a role in both deflecting comets away from the inner solar system, acting as a shield, and occasionally nudging Oort cloud comets into inner solar system trajectories. If Jupiter suddenly became 80 times more massive as a star, its gravitational sphere of influence, the Hill sphere, would expand enormously, and its ability to deflect comets would change dramatically. The Kuiper belt objects closest to Jupiter's new orbital location would be strongly perturbed. Long-period comets falling inward from the Oort cloud might be captured by the new stellar Jupiter, transforming from sun-falling comets into objects orbiting the new binary system in complex, chaotic trajectories. The rate of comet impacts on the inner planets could increase significantly, adding another layer of bombardment to the asteroid-driven impacts already discussed. But there's an even more exotic possibility related to the Oort cloud that is worth mentioning. The Oort cloud is so distant from the Sun that it is only marginally gravitationally bound. It sits at the very edge of the Sun's gravitational influence, where the gravitational pull of nearby stars and the tidal forces of the galactic disk are comparable to the Sun's own gravity. The addition of a second stellar body in the inner solar system would change the overall mass distribution and gravitational potential of the system in ways that could alter the stability of Oort cloud objects. Over millions of years, this could produce either a slow increase in the rate at which comets fall inward, a kind of geological timescale comet shower, or it could actually stabilize the Oort cloud differently, reducing the rate. The details would depend on the specific orbital dynamics of the new binary system and the galactic environment, and it is the kind of calculation that would keep planetary dynamicists busy for decades. Let's come back to something more immediate and more visceral: the experience of living under two suns over the course of a year. Because the geometry of this changes dramatically with the seasons, or rather with the changing orbital positions of Earth and the new stellar Jupiter as both orbit the Sun. And this geometry produces effects that are genuinely strange and beautiful as well as threatening. Jupiter currently takes 11.86 Earth years to complete one orbit around the Sun. Earth takes 1 year. This means that from Earth's perspective, Jupiter moves slowly through our sky, crawling through the constellations of the zodiac, completing one trip around the celestial sphere in about 12 years. When Jupiter is at opposition, directly opposite the Sun in Earth's sky, it rises at sunset and sets at sunrise, and is at its closest and brightest. When Jupiter is at conjunction, aligned with the Sun, it is not visible because it is above the horizon only during daytime. If Jupiter became a star, this same geometric relationship would apply, but the stakes would be vastly different. During the months when stellar Jupiter was at conjunction, when Earth, the Sun, and stellar Jupiter were aligned, the new star would be completely lost in the Sun's glare during daylight hours, and then rise just before dawn and set just after sunset, invisible in twilight. The Earth would experience, during those months, something closest to its current day-night cycle. Daytime dominated by the Sun, with genuine nighttime darkness available during the hours when both the Sun and stellar Jupiter were below the horizon simultaneously. But this window of real darkness would be brief, perhaps only a few hours per day at most, and even then stellar Jupiter's glow would be visible on the horizon. During the months when stellar Jupiter was at opposition, when Earth was between the Sun and stellar Jupiter, the new star would be high in the sky all night, delivering its constant orange-tinged glow to the night side of Earth. And during the periods of quadrature, when the angle between Earth, Sun, and stellar Jupiter was 90 degrees, the sky would be uniquely strange. The Sun would be setting in one direction while stellar Jupiter rose in another, and there would be a period in the evening when both luminaries were above the horizon simultaneously. The Sun still casting its full, white light while stellar Jupiter cast its dimmer, redder light from a different direction, creating the remarkable phenomenon of two sets of shadows pointing in opposite directions. The landscape illuminated from two conflicting sources, the world looking like a carefully lit stage. This dual shadow effect is something that science fiction artists have loved, and it's worth describing in more detail because it's genuinely beautiful and strange. On Earth today, shadows have one direction. They point away from the Sun. The uniformity of shadow direction is so fundamental to our visual experience of the world that our brains have evolved specific neural circuits to interpret shadow direction as a cue for object depth and spatial layout. When you look at a picture and see shadows going in two conflicting directions, your brain labels it as wrong or artificial. In a solar system with two suns, this cognitive dissonance would be the everyday reality. Every object, every person, every building and tree and mountain would cast two shadows, one sharp and pale from the bright sun, and one dimmer and orange-red from stellar Jupiter. Artists would have to unlearn everything they know about how light behaves. Photographers would work with completely different rules of lighting. Architects designing buildings around natural light would have to account for two sources of illumination coming from different directions at different times of day. Let's take a moment to explore something that most people never consider when thinking about this scenario. What would happen to the comets? The comets of our solar system exist in two main reservoirs. The Kuiper Belt, which extends from the orbit of Neptune outward to about 50 astronomical units, and the Oort cloud, a vast spherical shell of icy bodies that extends from about 2,000 astronomical units out to perhaps 100,000 astronomical units, nearly 2 light-years from the Sun. The Oort cloud is thought to contain trillions of cometary nuclei, and it is the source of long-period comets that occasionally fall inward toward the Sun on journeys of tens of thousands of years. Jupiter's gravitational influence currently plays a role in both deflecting comets away from the inner solar system, acting as a shield, and occasionally nudging Oort cloud comets into inner solar system trajectories. If Jupiter suddenly became 80 times more massive as a star, its gravitational sphere of influence, the Hill sphere, would expand enormously, and its ability to deflect comets would change dramatically. The Kuiper Belt objects closest to Jupiter's new orbital location would be strongly perturbed. Long-period comets falling inward from the Oort cloud might be captured by the new stellar Jupiter, transforming from sun-falling comets into objects orbiting the new binary system in complex, chaotic trajectories. The rate of comet impacts on the inner planets could increase significantly, adding another layer of bombardment to the asteroid-driven impacts already discussed. But there's an even more exotic possibility related to the Oort cloud that is worth mentioning. The Oort cloud is so distant from the Sun that it is only marginally gravitationally bound. It sits at the very edge of the Sun's gravitational influence, where the gravitational pull of nearby stars and the tidal forces of the galactic disk are comparable to the Sun's own gravity. The addition of a second stellar body in the inner solar system would change the overall mass distribution and gravitational potential of the system in ways that could alter the stability of Oort cloud objects. Over millions of years, this could produce either a slow increase in the rate at which comets fall inward, a kind of geological timescale comet shower, or it could actually stabilize the Oort cloud differently, reducing the rate. The details would depend on the specific orbital dynamics of the new binary system and the galactic environment, and it is the kind of calculation that would keep planetary dynamicists busy for decades. Let's come back to something more immediate and more visceral: the experience of living under two suns over the course of a year. Because the geometry of this changes dramatically with the seasons, or rather with the changing orbital positions of Earth and the new stellar Jupiter as both orbit the Sun. And this geometry produces effects that are genuinely strange and beautiful as well as threatening. Jupiter currently takes 11.86 Earth years to complete one orbit around the Sun. Earth takes 1 year. This means that from Earth's perspective, Jupiter moves slowly through our sky, crawling through the constellations of the zodiac, completing one trip around the celestial sphere in about 12 years. When Jupiter is at opposition, directly opposite the Sun in Earth's sky, it rises at sunset and sets at sunrise, and is at its closest and brightest. When Jupiter is at conjunction, aligned with the Sun, it is not visible because it is above the horizon only during daytime. If Jupiter became a star, this same geometric relationship would apply, but the stakes would be vastly different. During the months when stellar Jupiter was at conjunction, when Earth, the Sun, and stellar Jupiter were aligned, the new star would be completely lost in the Sun's glare during daylight hours, and then rise just before dawn and set just after sunset, invisible in twilight. The Earth would experience, during those months, something closest to its current day-night cycle. Daytime dominated by the Sun, with genuine nighttime darkness available during the hours when both the Sun and stellar Jupiter were below the horizon simultaneously. But this window of real darkness would be brief, perhaps only a few hours per day at most, and even then stellar Jupiter's glow would be visible on the horizon. During the months when stellar Jupiter was at opposition, when Earth was between the Sun and stellar Jupiter, the new star would be high in the sky all night, delivering its constant orange-tinged glow to the night side of Earth. And during the periods of quadrature, when the angle between Earth, Sun, and stellar Jupiter was 90 degrees, the sky would be uniquely strange. The Sun would be setting in one direction while stellar Jupiter rose in another, and there would be a period in the evening when both luminaries were above the horizon simultaneously. The Sun still casting its full, white light while stellar Jupiter cast its dimmer, redder light from a different direction, creating the remarkable phenomenon of two sets of shadows pointing in opposite directions. The landscape illuminated from two conflicting sources, the world looking like a carefully lit stage. This dual shadow effect is something that science fiction artists have loved, and it's worth describing in more detail because it's genuinely beautiful and strange. On Earth today, shadows have one direction. They point away from the Sun. The uniformity of shadow direction is so fundamental to our visual experience of the world that our brains have evolved specific neural circuits to interpret shadow direction as a cue for object depth and spatial layout. When you look at a picture and see shadows going in two conflicting directions, your brain labels it as wrong or artificial. In a solar system with two suns, this cognitive dissonance would be the everyday reality. Every object, every person, every building and tree and mountain would cast two shadows, one sharp and pale from the bright sun, and one dimmer and orange-red from stellar Jupiter. Artists would have to unlearn everything they know about how light behaves. Photographers would work with completely different rules of lighting. Architects designing buildings around natural light would have to account for two sources of illumination coming from different directions at different times of day. Now let me introduce a different angle on this story, because so far we've been discussing the physical effects of Jupiter's ignition primarily from the perspective of what would change on Earth. But there's an equally fascinating and slightly different question. What does the ignition of Jupiter tell us about the nature of brown dwarfs, about planetary formation in the broader galaxy, and about the conditions necessary for life? Because when you frame the question this way, you start to realize that the scenario we've been exploring is not just a thought experiment about one hypothetical solar system. It's actually a window into some of the deepest questions in contemporary astrophysics. Brown dwarfs, as we mentioned earlier, are objects that fall between giant planets and true stars, too massive for planetary classification, too light for sustained hydrogen fusion. The boundary between gas giant planets and brown dwarfs is technically set at 13 Jupiter masses, the minimum mass for deuterium fusion. But this boundary is increasingly recognized as artificial and somewhat arbitrary. The physical processes that form brown dwarfs and the physical processes that form giant planets overlap significantly. Brown dwarfs can form like stars, through direct gravitational collapse of a molecular cloud fragment. Giant planets form through core accretion in a protoplanetary disk. But the outcomes of these two formation processes can produce objects of similar size and composition. A brown dwarf of 15 Jupiter masses might be physically indistinguishable from a very massive planet of 15 Jupiter masses, even though one formed like a star and the other like a planet. This definitional ambiguity is sometimes called the brown dwarf desert problem, not the desert itself, which refers to the observed rarity of brown dwarf companions to stars at close separations, but the confusion about what these objects fundamentally are. What does this mean for our scenario? It means that when we ask, what if Jupiter ignited, we are implicitly asking about the boundary between stellar and planetary, about the process of star formation versus planet formation, and about whether these are really two distinct processes or two ends of a continuous spectrum. And current research increasingly suggests that they are indeed a continuum. There are super Jupiter planets, planets with masses of 5, 10, 12 Jupiter masses, that overlap with the lower end of the brown dwarf range. There are substellar companions that formed like stars but whose masses put them in the giant planet range. The universe does not observe the clean taxonomic boundaries that we create for our own convenience. This is deeply relevant to the question of life. Because if the formation of giant planets and the formation of stars is a continuum, then the question of whether a given solar system has a habitable planet also depends on where that system falls on this continuum. A system with a solar-type primary star and a brown dwarf secondary in a wide orbit might be just as capable of hosting Earth-type life as a single star system. A system with two red dwarfs in a tight orbit might have the most complex dynamics but also the most interesting combinations of habitable environments. The search for life in the universe. The astrobiological project that drives missions like the James Webb Space Telescope, the Habitable Worlds Observatory currently under development, and the Dragonfly mission to Titan, must grapple with the full complexity of stellar and planetary system diversity that the universe presents. And on the topic of the James Webb Space Telescope, it is worth noting that this extraordinary instrument, which has been operational since 2022 and which has already revolutionized our understanding of exoplanet atmospheres, galaxy formation, and the early universe, is perfectly suited to study the kind of objects we've been discussing. Brown dwarfs, being primarily infrared emitters, are ideal targets for the Webb telescope's infrared cameras and spectrographs. Webb has already observed numerous brown dwarfs, characterizing their atmospheric compositions, temperature structures, cloud patterns, and variability. One of the most remarkable Webb observations to date in this field involved the brown dwarf VHS 1256b, where the telescope detected an astonishing variety of atmospheric features including silicate clouds, water vapor, methane, carbon dioxide, and sodium. These observations are not just scientifically fascinating in their own right, they are directly relevant to our understanding of what a Jupiter-like body undergoing or approaching stellar conditions would actually look like. Let me take a moment to address some specific mythologies and cultural narratives about Jupiter that are relevant to this discussion, because the human cultural relationship to this planet is as rich and as old as human civilization itself, and it adds a layer of meaning to the scientific discussion that I think is worth exploring. In Roman mythology, Jupiter was the king of the gods, the supreme deity, the lord of the sky and thunder, the father of gods and men. His Greek counterpart was Zeus, who hurled lightning bolts and governed the cosmos with absolute authority. In Babylonian astronomy, the planet Jupiter was associated with Marduk, the chief god of the Babylonian pantheon, who defeated the primordial chaos monster Tiamat and created the world from her body. In Hindu astronomy, Jupiter is associated with Brihaspati, the guru of the gods, the planet of wisdom and divine teaching. In Chinese traditional astronomy, Jupiter was used as a year count object, the year star, because its roughly 12-year orbital period corresponded to the 12 animals of the Chinese zodiac. Across virtually every culture that developed astronomical traditions, and virtually every culture did, Jupiter occupied a position of supreme importance. It was the brightest object in the sky after the Sun, Moon, and Venus, and its slow, majestic passage through the constellations made it an obvious candidate for divine association. The idea of Jupiter becoming an actual star, of the king of the planets becoming an actual sun, a source of warmth and light, resonates with mythological themes for many cultures. The transformation of a powerful deity into a life-giving force, the ascension of the supreme ruler to a new level of cosmic significance, the second creation. These are narrative patterns that appear in mythology worldwide. In a sense, Arthur C. Clarke was tapping into something very deep in the human mythological consciousness when he wrote about the transformation of Jupiter in his novel. He was translating an ancient mythological narrative into the language of modern science fiction, and the resonance of that narrative is part of why the story has stayed so powerful in the cultural imagination. But there's a darker side to the mythology that is equally relevant. Many mythological traditions also contain stories of a second sun that was too bright, too hot, or too destructive. Stories of a world with two suns that was uninhabitable, that burned and scorched and died. In Chinese mythology, there is the legend of Ho-Yi, the divine archer who shot down 9 of the 10 suns that once burned in the sky, leaving only the single sun we have today, because all 10 suns together were destroying the world with their combined heat. The myth is a beautiful expression of the cultural intuition that one sun is exactly right and more than one is dangerous. In Greek mythology, the story of Phaeton, who took control of his father Helios's sun chariot and could not control the blazing horses, causing the chariot to veer too close to Earth and setting it ablaze, is another story about the danger of too much solar fire. These myths anticipate, in their own poetic way, the real astrophysical concern about what additional stellar radiation would do to a planet already perfectly calibrated for a single sun. Now let's explore something that I think will genuinely surprise you, and that changes the emotional tenor of this whole discussion. What if I told you that there is a credible scientific theory suggesting that our own solar system, the exact solar system we live in, may have been, very early in its history, a binary star system? Not with Jupiter as a star, but with a different second star that was later lost? This is a genuine scientific hypothesis, not fringe speculation. Dr. Konstantin Batygin and Dr. Gregory Laughlin, in work published in the early 2010s, explored the possibility that the early solar system had additional stellar companions that were subsequently ejected. More recently, work by researchers Sarah Sadavoy and Stephen Stoller at Harvard, published in 2017, suggested that most sun-like stars form in binary pairs, and that our solar system might once have had a binary companion. A star sometimes speculated about under the name Nemesis, that was ejected from the solar system in its early history. The Nemesis hypothesis has a long and fascinating backstory in paleontology and astrophysics. In 1984, paleontologists David Ropp and Jack Sepkoski published a paper arguing that mass extinctions on Earth showed a periodic pattern, recurring roughly every 26 million years. This supposed periodicity, now debated and not universally accepted in paleontology, was seized upon by several physicists, including Luis Alvarez, of the KPG impact iridium layer fame, and others, as evidence for a distant stellar companion to the Sun. The idea was that this companion, Nemesis, orbited the Sun in a very wide, elongated orbit with a period of 26 million years, and that each time it passed through the closest point of its orbit to the Sun, it would disturb the Oort cloud and shower the inner solar system with comets, causing extinction-level impacts. No evidence for Nemesis has ever been found, and its existence is not accepted by the mainstream scientific community. But the fact that the hypothesis was seriously proposed and seriously investigated by credible scientists is telling. It reflects the genuine scientific openness to the possibility that our solar system might once have had a companion star. The Sadavoy-Stoller work, which examined the distribution of binarity among young stars still embedded in their birth molecular clouds, found a very high binary fraction, close to 100%, for young Class 0 protostars, decreasing to around 70% for slightly older Class 1 protostars. They interpreted this as evidence that most stars begin their lives as binaries, with many of these binaries subsequently separating through gravitational interactions. If this interpretation is correct, and it remains controversial and actively debated, then our Sun might have had a binary companion in its earliest years that was ejected from the solar system, perhaps within the first 100 million years of the system's history. If so, the early history of our solar system may have been far more dramatic and far more complex than the standard single-star formation scenario suggests. This is relevant to the Jupiter ignition scenario because it means we may not be asking, what would it look like if our normal, single-star solar system suddenly became a binary? We may actually be asking, what would it look like if our solar system had retained its original binary character? And the answer from this perspective is something that is perhaps less exotic than it seems. Something that, in the broader context of stellar system formation, is actually closer to the norm. Let's turn now to the question of what a Jupiter star would mean for the possibility of life elsewhere in our solar system. Not just on Earth, but on the other planets and moons. Because this is where the scenario becomes genuinely profound from an astrobiological perspective. Mars is the obvious first candidate. Mars is currently a cold, dry, thin atmosphered world with surface pressures about 1% of Earth's. Its average surface temperature is about -60 degrees Celsius, though temperatures can reach +20 degrees Celsius at the equator in summer. Mars almost certainly had liquid water on its surface more than 3 billion years ago. We have abundant evidence of dried river channels, lake basins, and erosional features that require liquid water to explain. Where did that water go? Most of it was lost to space, driven off by the solar wind after Mars lost its global magnetic field roughly 4 billion years ago. Some is locked in the polar ice caps and subsurface permafrost. If Jupiter ignited as a star, the additional thermal radiation reaching Mars, which orbits at 1.52 astronomical units from the Sun, much closer to the stellar Jupiter at 5.2 astronomical units than Earth is, could be significant. Let's estimate. At Mars's distance from the Sun, the solar constant is about 590 watts per square meter, compared to 1,361 at Earth's distance. Jupiter's star at the distance of Mars from Jupiter, which varies, but averages several astronomical units, would deliver significantly less, perhaps a few hundredths of a watt per square meter. Over geological time, this is not enough to fundamentally change Mars's thermal state. But there's the radiation effect to consider as well. The additional ultraviolet and particle radiation from the stellar Jupiter, combined with whatever warming effect it provided, might interact with the Martian atmosphere in complex ways. And the gravitational perturbation of a stellar mass Jupiter would dramatically alter Mars's orbit over time, probably destabilizing it significantly. Mars, at 1.52 astronomical units, orbits closer to Jupiter than Earth does in relative terms, and its orbit is already known to be chaotic on timescales of millions to hundreds of millions of years in the current solar system. A stellar mass Jupiter would dramatically accelerate this chaos. Venus, on the other hand, is an intriguing case. Venus is already the most extreme climate case in the solar system. A world with a runaway greenhouse effect, surface temperatures of about 465 degrees Celsius, crushing atmospheric pressure 90 times Earth's, and clouds of sulfuric acid. The additional thermal input from a stellar Jupiter would be tiny in comparison to the Venus greenhouse effect, like adding a candle to a furnace. The effects on Venus of Jupiter's ignition would be dominated by gravitational perturbation of its orbit, not by additional thermal radiation. But it's worth noting that if Venus's orbit were significantly altered by the gravitational reshuffling, moved outward, say, to 0.8 or 0.9 astronomical units instead of its current 0.72, and if that orbital change somehow perturbed the Venus greenhouse enough to allow cooling, Venus might actually become a more hospitable world over geological time. This is very speculative, but it's the kind of possibility that the scenario opens up when you think carefully about all the indirect effects. Mercury, the innermost planet, would face the most severe orbital consequences of any inner planet. Mercury's current orbit is already one of the most chaotic in the solar system. The extreme eccentricity of its orbit and its proximity to the Sun mean that small perturbations can, over millions of years, push Mercury into a collision course with Venus or a solar infall trajectory. Simulations by Lasker and others show that there is roughly a 1% chance of Mercury's orbit becoming catastrophically unstable within the next 5 billion years, even without any perturbation. Add a stellar mass Jupiter, and that probability increases dramatically. In many scenarios, Mercury would be ejected from the solar system or flung into the Sun on relatively short timescales, millions to tens of millions of years rather than billions. Mercury's loss would be a dramatic event, but not one immediately felt on Earth. Now let's push even further out and think about the Kuiper Belt, the region of icy bodies beyond Neptune's orbit, home to Pluto, Eris, Makemake, Haumea, and literally hundreds of thousands of smaller icy objects. The Kuiper Belt currently extends from about 30 to about 50 astronomical units, and its structure is strongly influenced by Neptune's orbital resonances. A stellar mass Jupiter at 5.2 astronomical units would dramatically change the overall gravitational landscape of the outer solar system, affecting Neptune's orbit, and thus the Kuiper Belt's resonance structure, on relatively short timescales. The Kuiper Belt might be significantly depleted of material as objects were thrown out of resonance and into new, possibly destabilizing trajectories. Some Kuiper Belt objects might be sent falling into the inner solar system. Others might be ejected into the Oort cloud or beyond into interstellar space. The structural reorganization of the outer solar system would be significant and long-lasting. And then there is the question, the beautifully strange question, of what happens to stellar Jupiter's light and radiation reaching the trans-Neptunian objects, the Kuiper Belt, and even the inner edge of the Oort cloud. These regions are currently cold, dark, and frozen. The temperature in the Kuiper Belt is on the order of 50 Kelvin, about -220 degrees Celsius. The additional heat from a minimal mass red dwarf at 5 astronomical units would be almost completely negligible at these distances. But there is one effect that might be of astrobiological interest. On the surfaces of icy Kuiper belt objects, the chemistry driven by high-energy radiation from the sun, a process called radiolysis, produces complex organic molecules. The addition of a second radiation source, even a faint one, would contribute to this chemistry on the hemisphere of these bodies that faces stellar Jupiter. The effect would be tiny, but over geological time, even tiny effects accumulate. I want to return now to the human dimension of this scenario, because I've been spending a lot of time on the physical and biological effects, and not enough on what this event would mean for us as a conscious, self-aware, technology-wielding species. What would humanity actually do if Jupiter ignited? What would we think? What would we fear? What would we aspire to? And what would this event mean for the trajectory of human civilization? The immediate response would be panic, or at least intense anxiety. There is no precedent in recorded history for an event like this. A sudden, dramatic change in the solar system itself. Earthquakes, volcanic eruptions, hurricanes, even asteroid impacts are devastating but comprehensible in the framework of Earth's natural processes. A new star igniting in the solar system is something categorically different. It is a change in the framework itself, a disruption of the cosmic background against which all of human history has played out. The response of human civilization would be immediate and multidimensional. Scientists scrambling to understand what happened and predict the consequences, governments and international bodies mobilizing to coordinate the response, religious communities and leaders trying to provide meaning and comfort, financial markets convulsing in uncertainty, and ordinary people around the world simply standing outside and looking up at the new light in the sky with a mixture of terror and wonder. The scientific response would be extraordinary. Every telescope on Earth and in space would pivot toward the new stellar Jupiter. The Hubble Space Telescope, the James Webb Space Telescope, the Very Large Telescope in Chile, the Atacama Large Millimeter Array, the facilities of the Jet Propulsion Laboratory, the European Space Agency, the China National Space Administration, and every other astronomical institution on the planet would immediately begin observing and characterizing the new object. Space probes, any missions currently in the outer solar system, like the Juno spacecraft currently in orbit around Jupiter or any future missions in transit, would be repurposed as rapid response science platforms, their instruments turned toward the ignition event and its aftermath. The data flowing back would be unprecedented in its richness and its implications, and the scientific community would be working around the clock for months or years to make sense of it. But there would also be a profound question of survival preparedness that would immediately occupy governments and the international scientific community. The bombardment risk, the possibility that asteroid and comet impacts on Earth would increase significantly in the wake of Jupiter's orbital mass increase, would drive an immediate reconsideration of planetary defense strategies. Current planetary defense efforts, led by NASA's Planetary Defense Coordination Office and international partners, are primarily focused on detecting and potentially deflecting near-Earth asteroids that are already on close approach trajectories with Earth. The scope of that mission would need to expand enormously to address the new threat environment created by a stellar mass Jupiter disrupting the asteroid belt. The NEO, Near-Earth Object, surveys that currently catalog and track asteroids would need to be dramatically expanded, both in scope and in resources, to try to give maximum warning of newly destabilized asteroid trajectories falling into Earth-crossing orbits. The agricultural implications would be immediate and severe. Modern agriculture is not simply about growing food. It is about growing the right food in the right place at the right time, calibrated to existing climate patterns, seasonal cycles, water availability, and day length. Any significant change in the climate system, such as the nighttime warming and altered precipitation patterns that a stellar Jupiter would drive, would disrupt agricultural productivity in ways that could affect the food security of billions of people. The elimination of truly dark nights by itself would affect the growth cycles of photoperiod-sensitive crops, plants that use the length of the day and night as a signal to time their flowering, fruiting, and dormancy cycles. Short-day plants, which require more than a certain number of hours of darkness to flower, including rice, cotton, soybeans, sorghum, and chrysanthemums. might have difficulty flowering normally if the nights were never completely dark. Long day plants, which require long days to flower, might actually benefit from a faint additional light source that effectively extended their photoperiod. The net effect on global food production would depend on the specific intensity of the stellar Jupiter's night-side illumination and on how quickly agricultural systems could adapt through variety selection, greenhouse cultivation, or artificial light management. I want to explore one more genuinely fascinating aspect of the scenario that is almost never discussed in popular treatments. What would happen to the human relationship with space exploration in the wake of Jupiter's ignition? Because the ignition of Jupiter would transform the outer solar system from a hostile, radiation-blasted wilderness into something potentially more interesting and more accessible. In some respects, though far more dangerous in others. Currently, the main challenges of exploring the outer solar system are power and time. Solar power becomes ineffective beyond the asteroid belt because the solar constant drops off with the inverse square of distance. At Jupiter's distance, solar panels generate only about 4% as much power as they do in Earth orbit. This is why spacecraft sent to the outer solar system have traditionally been powered by radioisotope thermoelectric generators, RTGs, which generate electricity from the decay heat of radioactive materials. If Jupiter became a star, even a dim red dwarf, it would provide an additional power source for spacecraft in the outer solar system. Solar panels on spacecraft orbiting near stellar Jupiter could potentially generate modest amounts of power from the star's radiation. This is a small positive in a sea of negatives, but it's worth noting as a potential silver lining. More significantly, a stellar Jupiter would create a habitable zone of its own, a range of distances from the new star where liquid water could exist on the surface of a planet or moon. The habitable zone of a red dwarf star at the very lowest end of the stellar mass scale is extremely close to the star, on the order of a few million kilometers, which corresponds roughly to the orbital distances of Io and Europa from Jupiter. This means that Europa and possibly Ganymede might actually fall within or near the habitable zone of a stellar mass Jupiter. Not the Sun's habitable zone, where Earth sits, but the new stellar Jupiter's own habitable zone. If Europa were in the habitable zone of stellar Jupiter, its surface ice might melt over time, creating the open ocean we discussed earlier. And if life exists in Europa's current subsurface ocean, it would suddenly find itself on the surface of a liquid water world bathed in the faint red light of its parent star, a genuinely extraordinary astrobiological scenario. And here's a thought experiment that I want you to try at home, because it's one of the most illuminating ways to think about the implications of this entire scenario. Imagine you are a scientist in a few hundred years, perhaps living on a space station in Earth orbit, or on a colony on the Moon, or in a habitat on Mars. Jupiter has become a stellar body. The solar system has been reshuffled. Earth has survived, but it is different. Warmer at night, with more extreme weather, with a slightly altered axial tilt, with a night sky that is never truly dark. You look out through your habitat window at a sky with two suns, the bright white-yellow sun and the dim red-orange stellar Jupiter. What does it feel like? Does it feel like home? Does it feel like something to grieve? Or does it feel like a new beginning? A transformed solar system full of new possibilities, new destinations, new questions to answer. The answer you give to that thought experiment, I would argue, says something important about how you relate to the cosmos. It says something about whether you think of change, even radical, terrifying change, as primarily a source of loss or primarily a source of new opportunity. In the long history of life on Earth, the most dramatic physical changes in the planet's environment, the snowball Earth glaciations, the late heavy bombardment, the great oxygenation event when photosynthetic bacteria first filled Earth's atmosphere with oxygen and poisoned most of the life that existed at the time, the extinction of the dinosaurs. All of these were catastrophes from the perspective of the life that was living at the time. And yet, each catastrophe opened the door to something new. The oxygenation event killed most anaerobic life but made possible the evolution of complex aerobic life, including us. The extinction of the dinosaurs cleared the ecological stage for the diversification of mammals, including us. Change is terrifying. Change is sometimes fatal. And change is also always the engine of evolution. Would Jupiter's ignition be the end of human civilization? Almost certainly not in the short term. The initial radiation burst would be intense but manageable. The long-term gravitational and climate changes would be enormously challenging but not immediately lethal. Human civilization has proven remarkably resilient to environmental changes. Indeed, some evolutionary anthropologists argue that it was precisely the volatile, rapidly changing climate of the Pleistocene that drove the rapid expansion of human cognitive capacity, as surviving in a highly variable environment required flexible intelligence. The challenge of a stellar mass Jupiter would be far more severe than the Pleistocene climate swings, but the principle might apply at a civilizational level. Facing an existential challenge of unprecedented scale might catalyze human cooperation, technological innovation, and social reorganization in ways that we cannot fully imagine from our current vantage point. There is also a question worth addressing that some of you may have been turning over in the back of your minds throughout this discussion. Could human technology ever actually ignite Jupiter? Could we, through some application of technology that either exists or might exist in the future, add enough mass to Jupiter to push it over the threshold for deuterium fusion? The answer, based on current physics, is no, not even close. The mass needed to raise Jupiter to brown dwarf status is 13 times its current mass. That is 12 additional Jupiter masses of hydrogen and helium gas. There is no plausible technological mechanism by which humanity could gather, transport, or deliver that quantity of material to Jupiter. The engineering challenges are not merely really hard. They are physically absurd on the scale of any foreseeable technology. To put it in perspective, the entire mass of the asteroid belt is about 4% of the Moon's mass, and the Moon's mass is about 80 times less than Earth's mass, and Earth's mass is about 300 times less than Jupiter's mass. Even if we could somehow gather every atom of material in the entire asteroid belt and throw it at Jupiter, we would increase Jupiter's mass by a fraction of a percent. Utterly negligible. The mass of hydrogen and helium in the outer solar system, in the Kuiper belt, the Oort cloud, the interstellar medium, is vastly more than this, but it is also impossibly diffuse and impossibly far away to gather and concentrate with any technology we can imagine. Jupiter is safe from accidental human ignition for the foreseeable future. But what about the far future? What about a hypothetical civilization millions or billions of years more advanced than ours? Here we enter the realm of what physicist Nikolai Kardashev called Type 2 and Type 3 civilizations. Civilizations capable of harnessing stellar scale or galactic scale energy. A Type 2 civilization, by Kardashev's definition, is capable of harnessing the total energy output of its star. A civilization of that capability might conceivably have the technology to manipulate matter on solar system scales. Whether they would choose to ignite Jupiter is a different question. And it's actually a question that was explored by the physicist and speculative futurist Freeman Dyson, who wrote extensively about the possibilities for long-term intelligent life in the universe. Dyson speculated that a sufficiently advanced civilization might choose to disassemble the outer solar system entirely, converting its mass into energy or into habitable structures. Jupiter, in Dyson's framework, is primarily a resource, a vast reservoir of hydrogen fuel that a sufficiently advanced civilization might use to power itself for billions of years. Whether they would burn it as a star or use it more efficiently in fusion reactors is an interesting engineering optimization question with no obvious single answer. Let's come back to the present, and to the question of what we can learn from this thought experiment that is applicable to real science being done today. Because the "what if Jupiter ignited" scenario, despite being hypothetical, illuminates several genuine and important areas of current astrophysical research. First, it illuminates the science of binary star systems and their planetary architectures. Current missions and instruments, including the Kepler and TESS, Transiting Exoplanet Survey satellite missions, have detected several dozen confirmed circumbinary planets, planets orbiting both stars of a binary system. These systems demonstrate directly that planets can form and survive in binary environments. The study of these systems teaches us about the long-term orbital stability of planets around multiple stars, about the formation of planetary disks in binary systems, and about the range of environments in which life might potentially exist. Every piece of data from a circumbinary planet is directly relevant to the question of what would happen to Earth if Jupiter became a binary companion to the Sun. Second, it illuminates the science of stellar formation and the initial mass function, the statistical distribution of stellar masses at the moment of formation. Understanding why some gas clumps in a molecular cloud form stars of 10 solar masses and others form objects of 1/10 of a solar mass, and why some form brown dwarfs at the threshold of stellar ignition, is one of the fundamental problems of stellar astrophysics. The "what if Jupiter" question is really a version of the question, what determined Jupiter's final mass? What process stopped the gas accretion before Jupiter reached stellar threshold? The answer involves the interaction between the forming planet and the protoplanetary disk. The way that a growing protoplanet carves out a gap in the disk, slows its own accretion, and eventually gets stranded at whatever mass it has reached when the disk dissipates. Understanding this process better would tell us not just about Jupiter, but about the general question of what mass distribution of objects forms in protoplanetary systems, which has profound implications for the frequency of habitable planets in the galaxy. Third, it illuminates the science of exoplanet atmospheres and the search for biosignatures. One of the most exciting frontiers in current astronomy is the atmospheric characterization of exoplanets. Using spectroscopy to determine the chemical composition of the atmospheres of planets around other stars, and looking for biosignatures, atmospheric chemicals that would be extremely difficult to explain without the presence of life. Oxygen, methane, and nitrous oxide are among the candidates. The James Webb Space Telescope has already made remarkable progress in this area, detecting carbon dioxide in the atmosphere of the exoplanet WASP-39b, and publishing the first direct spectrum of a directly imaged exoplanet atmosphere. The scenario of Earth-like planet in a binary system with a giant planet star is exactly the kind of system that future generations of telescopes, perhaps the Habitable Worlds Observatory, currently in the conceptual planning stages at NASA, might target for atmospheric biosignature searches. If we ever detect biosignatures on a planet in a binary system with an architecture somewhat like our "what if Jupiter ignited" scenario, the knowledge we've developed through thought experiments like this one will help us interpret those observations correctly. Now let's take a dramatic and somewhat unexpected turn and talk about time. Because the ignition of Jupiter, if it could happen, would not be a one-time event. It would be the beginning of a new era in this solar system's history, one that would unfold over millions and billions of years, and the trajectory of that era is genuinely interesting to think about. A red dwarf star at the low end of the mass scale, roughly 80 Jupiter masses, or about 8% of the Sun's mass, has a main sequence lifetime that is extraordinarily long. While our Sun will exhaust its hydrogen fuel in about another 5 billion years, it is currently about halfway through its expected 10 billion year main sequence lifetime. A minimal mass red dwarf can burn for over 1 trillion years. The universe is only about 13.8 billion years old. So a minimal red dwarf ignited today would still be burning at the same modest rate in 100 times the current age of the universe. These are the most miserly, most patient, most enduring of all stars. They burn slow and low, like embers, for eons beyond imagining. If stellar Jupiter were such a minimal red dwarf, and if Earth's orbit remained stable enough for life to persist on its surface, then life on Earth would have not just the Sun's remaining 5 billion years, but an additional trillion-year backstop of faint stellar light from the second star, long after the Sun itself had evolved off the main sequence, expanded into a red giant, and eventually faded to a cold white dwarf. In the far, far future, billions of years hence, when our Sun is long dead and its remnant white dwarf is cooled to a dark cinder, if Earth somehow survived the Sun's red giant phase, which itself is a big if, the Sun may well engulf Earth as it expands. A restabilized Earth might still be illuminated by the faint red glow of stellar Jupiter, preserving some faint, dim warmth on a dark and ancient world. It is a haunting image. A sunburnt, ancient Earth, its oceans long evaporated by the Sun's red giant phase, perhaps resurfaced and reformed by geological processes over billions of years, orbiting a cold, faded sun remnant with a faint red ember in the sky. The ancient, patient, persistent stellar Jupiter, still burning its hydrogen reserves, providing just enough warmth to perhaps, maybe, possibly, sustain some form of chemistry that, over the trillion-year timescale of red dwarf stars, might give rise to something new. Something that looks up at the dim red sky and wonders what it all means. It is worth saying at this point that we have covered an enormous amount of ground, and I want to make sure we haven't lost the human thread of the story amid all the astrophysics. So let's step all the way back and ask the most fundamental question. What does this scenario, what does the very existence of Jupiter as a failed star, a planet that almost wasn't a planet, tell us about our place in the universe? The answer, I think, is both humbling and magnificent. It tells us that our existence is not inevitable. It tells us that the comfortable, stable, single-star solar system in which we evolved is not the only possible outcome of the forces that created our system. It is one outcome, perhaps a comparatively rare outcome, among a vast range of possibilities. It tells us that the specific balance of masses and distances and timings that characterize our solar system, a balance that includes Jupiter being exactly the size it is, not 13 times larger or 5 times smaller, sitting at exactly the distance it is, not 2 astronomical units closer or further, is a balance that matters, that has consequences for our existence, and that was not guaranteed by any law of nature to come out the way it did. This is sometimes framed as a variant of the anthropic principle, the idea that we can only observe the universe from the vantage point of observers, and therefore we should not be surprised to find ourselves in a universe with the particular properties that permit observers to exist. Jupiter had to be what it is, dark, cold, massive but not stellar, or else Earth might not have the biosphere it has, or might not have formed the same way, or might not have had the same long-term orbital stability. We are, in some sense, children of Jupiter's failure to become a star. Our existence depends not just on what happened, but on what didn't happen, on the paths not taken in the chaos of solar system formation 4.5 billion years ago. This should inspire a certain kind of reverence. Not religious reverence necessarily, though that is one possible response, but the secular reverence that comes from genuinely grasping the contingency of existence. The fragility of the conditions that made us possible. The extraordinary specificity of the path through possibility space that led to this moment, to you reading or listening to these words, on this planet, under this single sun. There is one more thing I want to discuss before we draw this story toward its conclusion, and it is something that cuts to the heart of what makes this topic so resonant and so important. It is the question of what the Jupiter ignition scenario tells us about the rare Earth hypothesis. The rare Earth hypothesis, first articulated by Peter Ward and Joe Kirschvink in their book, A New History of Life, and earlier by Ward and Donald Brownlee in Rare Earth, Why Complex Life is Uncommon in the Universe, suggests that the conditions necessary for the evolution of complex multicellular life are far more specific and far more rare in the universe than the conditions necessary for simple microbial life. The hypothesis argues that the emergence of complex life on Earth required not just liquid water and energy, the basic prerequisites for simple life, but an extraordinary suite of additional conditions. The right size star, not too large, not too small. The right distance from that star in the habitable zone. A large moon to stabilize axial tilt. A Jupiter-like giant in the outer solar system to provide gravitational shielding. A position in the galactic habitable zone, not too close to. The galactic center with its intense radiation and crowded stellar environment, not too far out with its scarcity of heavy elements, and many other factors. The presence of Jupiter in its current configuration, not too large, not too close, not a star, features prominently in the rare Earth argument. If Jupiter were significantly more massive, its gravitational influence might destabilize Earth's orbit or overwhelm the Moon's axial tilt stabilizing effect. If Jupiter were significantly less massive, it might not provide adequate gravitational shielding against cometary bombardment. If Jupiter were a star, the entire solar system architecture would be so different that the specific conditions that enable Earth's biosphere might never have arisen. The Jupiter ignition thought experiment thus becomes, when viewed through the rare Earth lens, a way of illustrating just how narrowly calibrated our solar system's configuration is for complex life, and how dramatically things would change if one parameter were adjusted beyond the range of current values. Now, it's important to note that the rare Earth hypothesis is contested. There are serious scientists who argue that complex life may be far more common than Ward and Brownlee suggest, that the specific conditions they enumerate as necessary are not truly necessary, that life's evolutionary creativity can find paths to complexity in a wide range of environments. The discovery of extremophiles, microorganisms that thrive in conditions of extreme temperature, pH, pressure, radiation, and chemical toxicity, has repeatedly extended the range of environments we consider potentially habitable. The discovery of hydrothermal vent ecosystems on the deep ocean floor, completely independent of sunlight, extended the definition of habitability in ways that have profound implications for life on other worlds. The discovery of complex organic chemistry in meteorites, in cometary material, in the interstellar medium itself, has shown that the building blocks of life are ubiquitous in the cosmos. None of this proves that complex life is common, proving that would require either detecting it or proving that its formation is inevitable from basic chemistry, neither of which we can currently do. But it does raise serious questions about how rare Earth truly is. What the Jupiter ignition scenario does, beautifully, is make this debate concrete and visceral. It's one thing to abstractly discuss whether complex life needs a non-stellar Jupiter-type giant for protection. It's another thing to trace through, step by step, all the ways in which a stellar Jupiter would change Earth's environment. The disrupted asteroid belt, the altered climate, the changed axial tilt dynamics, the permanent elimination of true night, the gravitational uncertainty of Earth's orbit, and recognize that each of these changes represents a stressor on the conditions that have allowed complex life to evolve and persist on Earth. Whether each stressor individually would be survivable, and whether the combination of all of them together would be survivable for a complex biosphere, is exactly the kind of question that planetary scientists and astrobiologists are now starting to model seriously. Let me also touch briefly on something that viewers and listeners often ask about in this context. What about the simulation hypothesis? What about the idea that our universe, or at least our solar system, might be a simulated environment created by some intelligence? The simulation hypothesis, popularized by philosopher Nick Bostrom and physicist Elon Musk, among others, suggests that if it is technically possible to create a detailed simulation of a universe or a solar system, and if sufficiently advanced civilizations exist or will exist, then there should be vastly more simulated universes than physical universes, and we should therefore expect to be living in a simulation. This is emphatically a philosophical hypothesis, not a scientific one in the sense that it is not falsifiable with current technology. But the Jupiter ignition scenario intersects with it in an interesting way. If we are in a simulation, then a simulation programmer could ignite Jupiter with a single parameter change, adjusting the mass of Jupiter above the fusion threshold. And in that case, all of the physics we've been discussing would play out exactly as we've described, with consequences for the simulated beings living in the simulated solar system that would be every bit as real and terrifying from their perspective as the scenario is from ours. The simulation hypothesis doesn't change the science, but it adds an extra layer of philosophical resonance to the question of why Jupiter is what it is, and whether the specific configuration of our solar system is the result of physics, chance, or design. As we approach the conclusion of this journey, I want to spend a few minutes on the most emotionally resonant aspect of the entire scenario. Not the physics, not the climate, not the orbital dynamics. The light. The simple, ancient, profound phenomenon of light. Light is the most fundamental way we experience the universe. Every photon that reaches your eye, from the first moment you open them as a newborn in a brightly lit hospital room to this very moment as you read or hear these words, is a messenger from the physical cosmos. A tiny packet of electromagnetic energy that has been generated somewhere, traveled through space, and interacted with the chemistry of your visual system to create the experience of seeing. The light from our sun has been making that journey 8 minutes long, for as long as life has existed on Earth. The sun's light created the conditions for photosynthesis, which created the oxygen in our atmosphere, which created the ozone layer that shields us from ultraviolet radiation, which allowed complex life to colonize the land, which eventually produced the organisms that evolved into us. We are, in the most literal and direct sense, made of sunlight. We are products of billions of years of a biosphere running on solar energy. If Jupiter ignited, we would be living under a second source of light. Not a more powerful one, not one that displaced the sun's primacy, but a second, dimmer, redder, more distant source that would add its photons to the world's light budget in perpetuity. Over billions of years, life on Earth, if it survived the disruptions of the ignition event and the subsequent gravitational reorganization, would evolve under this dual light regime. Eyes might evolve new sensitivities. Plants might develop new pigments. The entire photosynthetic and ecological machinery of the biosphere would gradually, over millions of years of selection pressure, adapt to an environment where both white sunlight and red stellar Jupiter light were available. What would those evolutionary products look like? We can only speculate, but the speculations are genuinely fascinating. Red-sensitive pigments might become more prominent in plant leaves, potentially making forests and grasslands appear darker, more absorptive of red wavelengths. Nocturnal animals, unable to find true darkness, might evolve reduced dependence on night camouflage or might evolve in entirely new behavioral directions. And the human visual system, already capable of detecting a remarkably wide range of wavelengths, might, over evolutionary time, expand its sensitivity into the near-infrared range to take advantage of the additional red photons from stellar Jupiter. These are millions of years timescales, far beyond anything we can observe directly, but they illustrate the profound way in which light, its source, its intensity, its spectral composition, its temporal pattern, shapes the evolution of life. We don't think about our sun as a variable controlling our biology, but it is. The specific spectrum, intensity, and daily rhythm of solar light has shaped every aspect of Earth's biosphere, from the wavelengths that chlorophyll absorbs to the depth of human sleep cycles to the colors of flowers evolved to attract specific pollinators. Change the light, change the world. And there is something in this that brings us full circle to the most personal dimension of this entire story. We are beings of light. Our consciousness arises from a brain that evolved under the light of a single yellow star. Our aesthetics, what we find beautiful, what moves us to awe, what triggers the experience of the sublime, has been shaped by the colors and patterns of a world illuminated by that one star. Sunrises and sunsets, moonlight on water, the diamond-scattered brilliance of a clear night sky, a double rainbow, the green of forest leaves, the blue of the ocean. All of these are products of a very specific light environment, and they carry emotional weight for us precisely because we have evolved in this environment, and our brains have been tuned to it over millions of years. If Jupiter were a star, all of this would be different. Not necessarily worse, different. The double shadows, the orange-tinted nights, the permanent warm glow on the horizon. The way sunsets would sometimes coincide with stellar Jupiter's rising, creating a sky blazing with two different colors of light. The way a storm at night would be illuminated from a different direction than we're used to. These would be, to beings evolved to experience them, simply the way the world is. They would be beautiful in their own way. They would produce their own art, their own poetry, their own philosophy. Because consciousness, whatever it is, wherever it arises, always finds beauty in the world it inhabits. That is perhaps the most remarkable thing about life. Its capacity to find meaning in whatever light is available. So here we are, at the end of this extraordinary journey through physics and philosophy, through mythology and mathematics, through the deep past and the speculative future of our solar system. We started with a question: what if Jupiter ignited? And we've traced it through layers of scientific understanding until it has revealed something much larger than itself. We've learned that Jupiter is made of the same stuff as the Sun, and that the difference between a star and a giant planet is a matter of quantity, not quality. We've learned that Jupiter would need to be 13 times more massive to even begin deuterium fusion as a brown dwarf, and 80 times more massive to become a true red dwarf star, and that these thresholds, while far beyond Jupiter's current mass, are not physically absurd in the context of the distribution of masses that form in stellar nebulae. We've learned that the ignition event would deliver a burst of radiation reaching Earth 41 minutes after ignition, causing auroral disruptions, ozone damage, and a permanent change to the night sky. We've learned that the steady-state emission of a red dwarf stellar Jupiter would be roughly comparable to a full moon in brightness as seen from Earth. Remarkable and strange, but not immediately lethal from the light component alone. We've learned that the gravitational consequences would be far more severe and far-reaching than the radiative ones, disrupting the asteroid belt, destabilizing the orbits of Mars and Mercury, altering Earth's axial tilt, threatening Earth's own orbital stability over millions of years. We've learned that Europa and Ganymede might actually benefit from a stellar Jupiter, potentially gaining liquid water surfaces and conditions more amenable to life. We've learned that the binary system that would result is actually a common configuration in the galaxy, and that Earth-like planets in S-type orbits around the primary star of binary systems are a genuine and observed phenomenon. We've learned that our solar system might actually have been a binary system in its early history, that the loss of a stellar companion may be part of our origin story, a cosmic divorce that enabled the specific conditions under which we exist. We've learned that the Jupiter ignition thought experiment is not merely a piece of science fiction fancy, but a serious window into questions about planetary system formation, binary star dynamics, astrobiology, and the conditions necessary for complex life. And we've learned that the specific configuration of our solar system, with Jupiter as a dark, cold, massive but non-stellar guardian of the outer planets, is one of the contingencies upon which our existence depends. But perhaps the most important thing we've learned is this: the universe is under no obligation to be comfortable for us. The universe is not configured for human convenience. The fact that we exist in a solar system with a particular configuration it has, a single, stable, yellow star, rocky inner planets, a large moon, a non-stellar giant guardian, a protective magnetic field, a rich and complex atmosphere, and about 4 billion years of biological evolution, is not inevitable. It is extraordinary. It is the product of a specific path through an enormous space of possibilities. And it is worth celebrating, not taking for granted, not assuming will persist forever, but genuinely, consciously celebrating. When you walk outside tonight and look up at the sky, you might see Jupiter. If it's visible, it will be that brilliant point of light, the brightest true star-like object in the sky, outshone only by the moon and sometimes by Venus. It will look serene, unremarkable, almost, just a bright point among the stars. But now you know what it is. You know that it is a world of hydrogen and helium, a world bigger than all the other planets combined, a world with a storm larger than Earth that has been raging for centuries, a world of 95 moons, including one with an ocean deeper than Earth's and one that might harbor life. You know that it is, at the deepest level of its chemistry, a star that never ignited, a fire with plenty of fuel but not quite enough kindling. And you know that its failure to become a star is, in a very real sense, the reason you are standing there looking at it. Look up at Jupiter. Look at that point of light. And feel, if you can, the appropriate mixture of wonder and gratitude that comes from knowing you are looking at a world that could have been a sun, and wasn't. And that this specific, marvelous, unlikely outcome is the reason that you exist to look at it, to question it, to study it, and to stand in the night air and feel something like awe. There is one final thought I want to leave you with, because I think it is the most powerful and the most lasting insight that this entire journey offers. We have spent this entire exploration talking about what it would mean if Jupiter became a star, about all the things that would change, all the systems that would be disrupted, all the dangers that would arise, all the possibilities that would open up. And running through all of it, like a thread of gold through a dark tapestry, has been the implicit recognition that change, even cosmic scale change, is not the end of the story. It is a new chapter. Life on Earth has survived 5 major extinction events. It has survived the transition from an anoxic to an oxygenated atmosphere that killed most of the life that existed at the time. It has survived impacts from asteroids and comets large enough to vaporize the ocean's surface layers. It has survived ice ages that buried the planet in glaciers from pole to equator. It has always found a way. Not the same way, not the same life, not the same ecosystem, but a way. Some form of life has always persisted, and from that persistence, evolution has always built new complexity, new diversity, new beauty. If Jupiter ignited, life would face its greatest challenge since the formation of the solar system. Many species would perish. Many ecosystems would collapse. The world would be, for a long time, harder and stranger and more violent than it is today. But life would persist. And over millions of years, in the light of two suns, a white-yellow primary and a dim red companion, something new would grow. Something we cannot imagine. Something that would look up at its two suns and wonder how it came to be. And perhaps, in some far future, that something would ask, what if one of these suns hadn't been here? What would the world look like with only a single star? And the answer, the extraordinary, improbable, beautiful answer, would be something like us. This is what the universe does. It creates conditions. It destroys them. It creates new ones. And in the space between destruction and creation, in the trembling gap between what was and what will be, life finds its way. Consciousness finds its way. Wonder finds its way. And the questions never stop.